So shall we start now?
If we just give maybe like just 1 or so minute or something for people to join.
Okay.
Yeah, we've got people coming in now. Just to let everyone know, the webinar will start shortly. We're just letting people join.
Is there some way to display the current schedule?
It should be on the screen now. I've got the starting sliders on there with the schedule. Okay, I think we can go ahead and start.
Okay. Okay, let's start this webinar today. This is sponsored by the journal Machine Learning in Science and Technology, which is a new journal in IOP, try to bring together the field of machine learning and science discovery and technology advances. So now let's first have the publisher, Sharam, to introduce this journal.
Thank you very much. So many thanks for joining us today. My name is Sarah Bebbington, and I'm the publisher for IOP Publishing. And so I just wanted to very briefly tell you about IOP Publishing and a little bit about one of our newest titles, which is Machine Learning, Science and Technology. I'm just waiting for the slide to move on. So IOP Publishing is a society-owned scientific publisher, providing impact, recognition, and value for the scientific community. As a subsidiary of the Institute of Physics, IOP, any financial surplus made by IOP Publishing goes directly to the IOP and assists their mission to help everyone build their knowledge of physics and to provide professional support for physicists. So as we said, today's webinar is brought to you by the journal Machine Learning, Science and Technology. It's one of our newest titles, and it's a multidisciplinary open access journal publishing research of the highest quality relating to the application and development of machine learning for the sciences. We wanted to arrange this webinar today to showcase the breadth of the field, and I'd like to thank Professor Zhai for firstly agreeing to chair our session today, and secondly for organizing our great lineup of speakers. Thank you all for joining us. Everyone listening today as an audience member is welcome to submit questions for our chair or our speakers. These can be submitted via the questions box on your screens. And there is also a leaflet that you can download at any point during the webinar, which has more information about the journal. I'd like to hand over now to the Editor-in-Chief for Machine Learning and Science and Technology, Professor Anatol von Lillefeld.
Good morning, everyone. It's really great pleasure to be here and to talk to you. I'd like to start off by thanking MLST and Sarah, and in particular Professor Zhai for organizing this whole thing. I have a couple of slides I'd like to share, which so I'm missing the button. Let's see. Oh yeah, no, you can see this. Can you see my screen now? I'd like to.
At the moment, we can't see the full slides, but we can see. I think we're.
Okay.
Yeah, we can see the full screen now.
Right. All right. So I'd like to start by telling you that I'm just a normal professor. I'm doing research, and usually my talks start off like this. So I'm running a lab where we use machine learning and perturbation-based, quantum mechanics-based approaches to explore chemical compound space, right? And so this is sort of where I come from. So this would be my usual beginning slide. And I have a lab with people. We just moved from University of Basel to University of Vienna in Austria, and these are the people and the funding agencies. So this is maybe to convey the idea that this is really an academic enterprise, right? We are not all the editorial board members are academics and professors in the field. Now, of course, we need the professional staff from IOP Publishing to take care of the important technical things, but in terms of contents, it's really academics driven. Now, regarding my own contributions, I don't have much time, and I'm not meant to talk about you today because it's about China really, and efforts going on by Chinese scientists. But just very briefly, we just recently edited a book, collaborators of mine with many contributed chapters in the field. So this could be interesting, and my group is also at the origin of Python open source code that you can find on the GitHub, which we call the QML code. So this is accessible for anybody. Now, regarding this journal, I'd like to tell you a couple of words. This journal is, and Sarah mentioned that already, is a multidisciplinary journal. We try to get open access, get high visibility for open access, and particularly in 2020, the article processing fees are being waived. So it's also a very new journal, and I'd like to just briefly tell you about where it comes from. So when I was approached by the senior editors in IOP Publishing, my first question was, why do we need yet another journal? And we, as you know, we have so many journals, and it's hard to keep track. And so this was my main reservation in the beginning. But I did realize through work, and we've been using machine learning since 2010 for 10 years now. In my field, and I noticed that there is sort of a lack of a good venue for technical machine learning progress. So not necessarily when you really develop new math, right? Then you would have the statistical learning journals, but or conference proceedings. But if you develop a new technical advance which furthers your field, there's really no venue that would let people who work maybe on similar problems but in other fields, who would let them know what you have done and maybe profit from that. And so that was really my main motivation, that we can go across these interdisciplinary boundaries and share the mutual advances we've made in pushing machine learning related techniques further. So it's really for sort of technical machine learning progress, and it's quite interdisciplinary. But the whole thing, what was also very important to me is that this is subject to an open source spirit. So the open access component is very important. That this journal also allows to share data and code easily, and that the whole thing is not for profit maximization, right? And so the Institute of Physics and its publishing subsidiary seemed like a very good fit for that. If you're not aware of this institute, it's a learned society based in the United Kingdom, and it's really to advance physics education and research, and also its applications. They also have a couple of career advices and professional qualifications, which is maybe less relevant for us, but then there's also the IOP's publishing company, IOP Publishing, which really is the main place where the journal comes from. Since this was has always been an academic, the editorial board and its composition is key. And so I was really honored and pleased and delighted that so many outstanding academics agreed to join the editorial board. So this is an overview you see here. The board is still very young. If you know highly qualified members of the scientific community who might be interested in serving, do not hesitate to propose them to us. We are still seeking to grow the board and complete it to cover all the interdisciplinary aspects where machine learning might play a role in the hard sciences. So you see various representatives of these communities, maybe some names or some institutions ring a bell. Of course, I should very much highlight Professor Hui Zhai for his leadership in this webinar. So it's really a pleasure to work with the board. We unfortunately, due to the pandemic, we could not have a board meeting in person yet, but this is something we are planning for, and we did have some virtual meetings where we update on things. We also seek advice from the editorial board on strategic directions, and editorial board members are contacted when there are cases where the reviewing is not obvious, the outcome is not obvious, and so you need to make some executive decisions, and for those things the editorial board members are very important. There's another role that now when you submit to MLST, there's a possibility to also select a board member in case that there is some sort of dispute, so that you make sure that if there is upon submission as an author, if there is some dispute with the referees, that it goes directly to the editorial board member of your choice, so that you know that somebody competent has a look at it. Now, as Sarah said, this journal was really, it started last year, and the first issue came out only this year, and so I had the pleasure to write the editorial for this journal, and as the abstract says, it's really, I think it's a timely moment to have such a journal. There's an ever-growing digitalization and computing capability, and data has become increasingly abundant because of that. And to make use of data in a rigorous way, of course, we require statistical learning techniques, and this has enabled many technologies already in society, but now it's really the question of how can we use that also to further scientific progress, right? This journal was really conceived then also and designed and through many discussions throughout the community, and it's really its ambition to serve that new sort of overlapping interdisciplinary community that shares as a common denominator that we all want to use machine learning to do research. Now, in terms of scope, then MLST is really a multidisciplinary journal. It bridges the application of machine learning across the sciences. And the key thing is, of course, it's still a scientific journal, so any new scientific conceptual advances, and in particular, IOP is an institute of physics, so we want physics-based progress, right? It's not the journal to send your latest cats and dogs neural net, but rather something where thanks to physics inside, you make progress on your machine learning architectures. Articles are really expected to either make conceptual or methodological advances in machine learning with applications. Alternatively, you can also simply advance the state of the art of given machine learning driven applications in a specific science. So if you learn about the latest deep neural net that was successfully applied in one science, and you now apply it for the first time in your science, that's of course extremely interesting to see that it works there as well, and maybe outperforms other state-of-the-art techniques. Now, in our latest board meeting, we did have a discussion about the scope, and this is sort of a shortened summary of this, but basically the point was made that we should not require applications to be part of the journal, right? If there is a methodological advance with an application, that's wonderful. If there's a methodological advance by itself without a major application, that should be fine as well. So this was not very controversial, but it would extend the current scope. So in the editorial, what's highlighted here in pink was not part of the scope yet. So this is a slide Sarah gave me on how the journal has been faring so far, and we've also been surprised by the amount of very solid research papers that have been submitted, and many of those are actually of sufficient quality as judged by the reviewing process to be accepted. And you see that by now we average on something like 10 papers a month, which is very solid for a new journal. So I'm told, so this is also the first time I'm serving as an editor-in-chief, but the actual targets were lower, as you can see at the bottom, right? So this journal has been surpassing expectations, and I think it's due to the editorial board, its quality, and it's due to the field being very active and exciting, and there's a lot of enthusiasm. MLST also has various paper article formats, and one effort is also to have focus issues. And so board members or invited guest editors can collect a team of, or can assemble a set of representatives and communities and focus on certain topics. And you see here an overview of a couple of focus issues which are currently underway, and they're making great progress, as you can see by the status, the number of accepted and submitted papers here. MLST also helps with outreach and visibility through a Twitter handle. So if you publish in MLST, they typically do some advertising on Twitter for your paper, and I have found this very helpful. It really increases the visibility to other scientists who, of course, also have to be active on Twitter. But there is I would say, a sizable group of serious scientists who actually are on Twitter, and if you can filter out all the other noise on Twitter, then this can be actually very helpful. So with this, I'd like to conclude this little intro. I hope you found that interesting. I look very much forward to the talks coming up now, and I would like to thank you very much for your attention.
Okay, Thanks for this wonderful introduction of the journal. Actually, I don't find any questions in the question panel. Maybe we go to the talks. So yes, in this afternoon we will have 3 talks. The 3 talks will cover different aspects between machine learning and the science. The first talk will given by Professor Yu from University of California, San Diego. Actually, Yi Zhuang and I have a very similar research field and interests. We all are working on machine learning and quantum matters. So I think Yi Zhuang will share with us his view of how this machine learning can help us on physics, especially quantum many-body physics problems. And the second talk will given by Dezhen Xue. He's a young scientist on Xi'an Jiaotong University. I think his major research area is on materials science, and he will talk about how using the machine learning method to help us in searching new materials with target properties. And the last talk is given by Ge Wang. He's a very senior scientist on using machine learning for medical images. He has a lot of very important contribution on CT images since 90s. And he also has done a lot of important work on using deep learning to recognize this tomographic imaging from CT. So I think this 3 talks. Oh, by the way, both Yi Zhuang and Professor Ge Wang are also the editorial members. So I think these 3 talks nicely covers different aspects, and you can from this and you can tell that this journal really has brought aspect to cover different directions between machine learning and the sciences. With this, let's first welcome Yi Zhuang from University of San Diego to give his talk.
Yeah, thank you. Thanks, thanks Hui Zhai for the introduction, and thanks for the for the invitation. And then, so today I'm going to talk about some of our works in this field. It's all about how to use machine learning to model physics phenomena, in particular in quantum many-body physics. So I'm Yizhuang Yu. I'm an assistant professor at University of California, San Diego. And my background is basically condensed matter physics. So in condensed matter physics, central theme is about the emergent phenomenon, how you can put single particles together and then their collective behavior will emerge into a non-trivial collective behavior can emerge under the interaction between these particles. So under this theme, a lot of things can emerge. For example, like quasi-particle can emerge in material, and also electromagnetic force can emerge, and even space-time can emerge in certain models, or even gravity can emerge. So these are all emergent phenomena in condensed matter physics. But if we think about these physics theory themselves, then we may say, oh, these theories themselves are also emergent phenomena. They are the emergent phenomena in the neural network of human's brain, or more generally, actually in the social network of physicists. So how to understand this emergent phenomena of physics theories themselves either in the neural network or in the social network or in complex network? I think it's a very interesting question, and then I think it's also one of the ultimate goal for us to understand the origin of intelligence and the emergence of scientific theories. So along this direction, basically, I think one ultimate goal is, can we have an AI physicist or AI scientist one day? And then the question is more concretely is about, can AI help us to model physical systems or even to formulate physics theories? So of course, we are still very far from perfectly answering this question. So currently, of course, our AI machine learning technique has not achieved this generic AI. It's always limited in very special areas. But I think for us, for me at least, I'm interested in trying to look into different fields in physics and see how can we teach machine to learn physics. And maybe one day, if the machine learns enough, then maybe it can create new physics by themselves. So today I'm going to talk about three works, or briefly introduce them, which are in about machine learning quantum mechanics using a recurrent autoencoder, which was in collaboration with Professor Hui Zhai and his student Wan Ce. And then also machine learning renormalization group using flow-based degenerative model, which was in collaboration with my student Hong Ye and Professor Lei Wang and his student Shuo Hui, and also machine learning ADS-CFT, which is a latest work, which we use neural ODE. And then this work is in collaboration with Hong Ye and Koji. And then this work has been accepted by Machine Learning Science and Technology recently. So the first topic is about learning quantum mechanics. So the idea is, suppose quantum mechanics haven't been formulated so far. Let's suppose. But amazingly, we know how to do cold atom experiments with Bose-Einstein condensates. So the experiment basically is loading atoms into a potential. So you may have a designable potential profile, but if you load the atom into the potential and cool down to the ground state, there can be a distribution of the density of the atom. So, so one can measure the density given this potential. So if you prepare a different shape of the potential, the density will also change accordingly. And since we learn quantum mechanics, and we know that this density and potential, the mapping between them, is governed by the quantum mechanics. It's by solving a Schrodinger equation. You have a potential, you solve for wave function, and if you square the wave function, that's density. But suppose machine was only exposed to the potential and density data. Can machine somehow come up with a theory, try to explain how the density should be reshaped in response to different potential? And can this theory eventually be similar to quantum mechanics, or may quantum mechanics be rediscovered in this process? So in order to try out this kind of problem, we basically design a translation machine, which is we are motivated by natural language processing, where a machine can be used to translate from one language to another language. So that's a sequence-to-sequence mapping. So the problem we want to solve in this task, the task is also a sequence-to-sequence mapping. Basically, given the potential sequence, consider the system is a one-dimensional system, so potential is a sequence, density is also a sequence. Try to build a translator to translate the potential to density, basically. So the technique we'll use is kind of standard. We have some creation there, but the overall framework is just a recurrent neural network, which basically maps the sequence to sequence. And it has many trainable units. And eventually, after training, what we can see is that, for example, this picture shows the blue line is the potential shape of the potential, and the green line is the target density, and the red dashed line is the output. So basically, machine by trying to use a recurrent neural network to translate the potential into certain density and try to bring that density to the target density, we can train a machine that pretty much can perform this task. But that's not the end of the story. We want to ask, after the machine can perform this task, can it learn any physics? It must have learned some physics behind this task. So, but unfortunately, originally we think that physics must be hidden in these hidden variables in the recurrent neural network. But after opening up the neural network and trying to look for this physics, it turns out to be rather difficult. So that's why we designed a second machine, which is a recurrent autoencoder, which actually try to understand what the first machine is thinking. So basically, it takes the hidden variable in this of the recurrent neural network from the first machine and try to compress it and use the compressed signal to predict the behavior of this hidden variable in future prediction steps. So then, because it reaches the compression, so we can have some compressed representation. The idea is try to use this autoencoder to extract the most essential variables in this hidden in this latent space that describe the process of translation. And because we know from quantum mechanics that the most important variable should be the wave function, because you need to calculate the wave function in order to make this prediction. So that's the most important intermediate variable. And then indeed, we did the experiments, and what we found is that if we keep squeezing the latent dimension of this second machine, and we find that the second machine, if the latent dimension of the second machine reduced to one real variable, then the loss function cannot decrease. But if you have two or more variables in the second machine, then basically the second machine can pretty much capture how the first machine is thinking. So so that means there are only two essential variables that describe this prediction process or this translation process. So that two real variables, if we plot them out, it turns out that these two real variables correspond to the real and imaginary part of the wave function. So we can see that the first machine only interact with data, which is about the potential and density, which has nothing to do with at least not explicitly about the wave function. But using the machine learning approach, machine can kind of summarize what's the most important variable and even find what's the update rule between the variable, which turns out to be the Schrodinger equation. So this is an example of rediscovery of quantum mechanics in machine learning using machine learning techniques. So that's one of our first steps towards maybe machine can discover new physics, hopefully in the future. So currently it's still discovering this old physics. And then another topic is about machine learning renormalization group. Renormalization group is a technique in quantum field theory, which is progressively cross-graining the field configuration, try to extract the most relevant feature of the field configuration. But when we talk about renormalization group or RG, so what is the most relevant feature? There's even not a definition of what feature should be most relevant, because the most relevant feature should be model dependent. For example, if you consider an Ising model, a Stagman model of spins, basically, it depends on whether your Ising model is ferromagnetic coupled or anti-ferromagnetic coupled. Because for a ferromagnetic Ising model, the most relevant feature should be the uniform spin magnetization, basically, because that's like the ground state configuration. And the anti-ferromagnetic Ising model should be the stagger spin moment or magnetization. So, or if it is a random Ising model, then the most relevant feature is kind of more random. It's hard to say. So so also we have other scheme of RG, like in the momentum space, we can, in field theory, people do momentum space RG. So there are so many different RG schemes. Like in momentum space RG, what is relevant is the low energy degrees of freedom. So what's the criterion of this relevance? Either it's uniform in terms of pattern or low energy in terms of energy. So we try to come up with a criterion that the most relevant feature should be the feature. So instead of trying to define the relevant feature, we try to define what's the irrelevant feature. We treat RG as as a local cross-graining local transformation, and the transformation should throw out some information that is irrelevant and keep those information that is relevant to the next level. So the irrelevant information should look like noise. So that's basically the idea. So the idea to find RG scheme using machine learning is trying to use machine learning neural network to parameterize generic transformations and require that this transformation can gradually throw out irrelevant informations which correspond to noise. And then if you train the machine to do such kind of mapping, then eventually the machine can learn the optimal RG scheme based on the model action. So basically we design a machine learning architecture, which is using these ideas of generative model, because by throwing out noise in each RG step, if you consider the reverse RG step, then that's like you combine the configuration with noise and try to create fine-grained configurations. So basically, a renormalization group is actually the opposite of a generative model. So if we can train a generative model that starts from random noise and reproduce the field configuration according to the Boltzmann distribution, then we pretty much also train the renormalization group transformation. So using this idea, basically, we start from some random noise, and then we use a trainable nonlinear function G, and this G is like a generative function, and transform all this random noise into a field configuration. And we require that this field configuration under this transformation, it will have a new distribution. So the random noise will have a prior distribution. Under the transformation, the random noise distribution will be deformed by the Jacobian, and then it creates a new distribution for the transformed field distribution. And the field distribution should try to match the target distribution given by the action of your quantum field theory. And then this matching of different probabilities is achieved by minimizing the KL divergence between these two distributions. So basically, we end up with designing a hierarchical network such that it can map a lot of random variables in the so-called holographic bulk into the holographic boundary. And the machine learning goal is to make the boundary distribution as much as possible similar to the Boltzmann distribution of the quantum field theory, let's say. So in this way, indeed, we can train the machine and then find this mapping. And then after finding this mapping, we do a check. So basically, we tweak the most deepest hidden variable and see what's the difference in terms of this generated configuration. What we found is that this model that we use is a XY model. We basically try to generate XY configurations. So what we found is that if we tweak the most IR component, it corresponds to a global rotation of all the little spins in the same direction. So that means the machine automatically finds the ghost town mode as the most relevant degrees of freedom in an XY model, which is exactly the low energy physics. Although in this procedure, we never tell the machine what is low energy or whether you need to look for uniform patterns. There's no such kind of hint. Just by training a generative model, machine can find the RG rules. And this RG rule can be useful because if you make a local update in the holographic bulk, then that broadcasts into a global update through this nonlinear map on the boundary. So by boundary, I mean this holographic boundary. So that can be used to improve the Monte Carlo simulation efficiency, because we all know if we want to simulate critical system, it suffers from critical slowdown in the Monte Carlo simulation. But if somehow we can simulate the system in the holographic bulk, because the bulk theory is kind of massive, so it doesn't suffer from this slowdown. So it will have also be useful in the future, I think. And then maybe the last topic is a recent work about machine learning holography. Holography is an idea that comes from ADS-CFT correspondence, which is saying that a quantum theory defined in the let's say 4-dimensional space have a 5-dimensional gravity due. And then the question is, given the quantum theory on the on the so-called holographic boundary, can we kind of infer what is the gravity theory in the bulk? So I think that's also a very interesting question for machine learning. Try to ask the machine, can you discover any gravity theory that even physicists haven't figured out in this ADS-CFT duality? So basically, we try that on a holographic QCD, quantum chromodynamics, which we use. We collect some QCD data by Monte Carlo simulation, and then that serves as our input data. The data that we collect is basically the response function, how the quark density responds to the mass deformation of the QCD theory. So that's what we collect on the boundary. That's about the quantum system. So we try to ask the machine to establish a gravity theory in the bulk, following the ADS-CFT correspondence, where there are several unknowns. For example, what's the geometry in the bulk? What should be the metric? And what should be the interaction between these meson fields in the bulk? It's all unknown. But nevertheless, you can always use a neural network to parameterize all these unknown functions and ask the machine to learn it. And then this learning is like, you need to start from the boundary and solve this differential equation, and then try to match this boundary response theory. So it requires you to, the loss function basically is like, you need to solve the differential equation and check whether the solution match the boundary condition or not. So it requires the loss function to have a gradient propagating through the ODE solver, the differential equation solver. So that's a technique that is actually recently developed as neural ODE that allows us to train a differential equation, not only train a neural network. So in that way, basically, we can train the machine such that it matches the response function. So this picture shows the data that we collect from the Monte Carlo simulation, which is the green line, and then the machine predicted result is the blue line, which is pretty much overlapping. And then by training the machine to make this prediction, actually, we can find what's the emergent metric, what's the geometry in the bulk. And the geometry in the bulk is not entirely trivial. It has certain bottleneck, which is associated with the binding of quarks in this ODE theory. So there's certain length scales associated with that. So that's pretty much the story. And then so in all these tasks, I think the general theme is that we ask the machine to perform certain tasks. But after performing the task, we didn't just use the machine as a black box to process our data. We want to open up the machine and see what kind of physics it has learned. And I think so the last project, this neural ODE project, we submit our paper to machine learning science and technology, and then I think it's a very appropriate journal for this kind of research. I discussed when I discussed with my collaborators, we think that if we submit to usual physics journal, they want to appreciate the usage of neural ODE. But if you submit to any machine learning kind of a journal, then they may lack the understanding of the physics background. So I think this is a very nice combination of machine learning and physics. And this journal is also created specifically for this kind of interdisciplinary studies. So okay, so that's what I want to say. Thank you.
Okay, let's thank Yi Zhuang for this very wonderful talk. And I also just heard from that actually in another platform, the Koxiang, the co-share platform, there are now more than 2,000 people attending this webinar. So that's actually a very exciting activities. But I don't know whether they are now, because I think most people in China now they are not using this go-to webinar platform. They are rather using co-share, which is co-share platform, which is a local Chinese platform. So I don't know whether questions from there, or maybe someone is monitor the monitor that co-share platform. Any question from co-share?
It is being monitored, so we'll just check if there's anything coming through.
Okay, I think if not immediately, maybe we can go to the second questions, and if we have some other questions, we can from co-share, we can to any of speakers, maybe we can ask later. And now let's.
I have an immediate question, if I may.
Okay. Yes.
Yeah.
So I thought this was wonderful, and I also like the example you gave in the beginning with the Bose-Einstein condensate, and there I had a question, right? So you sort of rediscovered the importance of first order derivatives, but shouldn't it also include second order derivatives for your kinetic energy operator? And shouldn't you also discover the potential, the electron interaction operator, like 1 over the distance for the electron? So what are your thoughts on this? Would there be one day the possibility to actually have that, or get the full Hamiltonian out of it?
Yeah, indeed, that's very good question. And then we're also thinking about this. So currently for this paper, we only discuss like a free particle. It's like a single body problem. It's all described by a BEC, only one single wave function. So there's no interaction currently involved. But I think in the future, definitely we can involve interaction, not only for bosons, also for fermions, and hopefully it can learn maybe the density functional theories out of that. That's one hope. So yeah, definitely. That's
actually, I actually remember when Yi Zhuang and I initially begin to talk about this project, we are aiming at discovering something like DF density functional theory. Yeah, that's certainly the one of the goal to include the interactions. Yeah.
Yes.
And also, I think this is a nice structure to separate out the learning part and the interpretation part. Is also very useful, and it can be applied to many different problems. To try to, on one hand, you use the machine to learn something, and on the other hand, you're using another machine to make interpretations. And this kind of structure maybe can be used to many other problems.
Right.
Okay, since we just mentioned the density functional theory, now let's hand the talk to our second speaker, Dezhen, to talk about some material science. Okay. Yes, Dezhen, you can speak now.
Okay, thank you, Professor Zhai. It's my great honor to give this talk. Actually, I'm a experimentalist, so today I'm going to share some of our baby steps to use machine learning in searching for new materials with targeted properties. So I'm Dezhen Xue from Xi'an Jiaotong University. My title today is Active Learning in Searching for New Materials with Targeted Properties. So first of all, I would like to thank my collaborators in Jiaotong University, Ding, Sun, Zhou, and also my collaborators in US, Terrell Luckman and Prasanna. And several work was did by my students, Rui Hao, Yuan, and Yunfan. I would like also acknowledge the financial support from the Chinese government. Okay, so just now Yizhuang talked about the physics, the condensed matter physics. So my research area is material science. So in material science, we always face some challenges. One of the most important one is that we have a very high dimensional discovery space, but only we have a very small fraction explored. We only have a small amount of measured properties. So the material properties can be influenced by the chemical compositions, what kind of structure it is, or it can have many different phases. And we can also have the different processing conditions. We can forge it, we can raw it, or we can do different heat treatment. So those factors all influence the property of the material. So finding a new material is actually an optimization problem in such a high dimensional search space. So we say that the searching is like optimization. We want the property Y as large as possible. So if the search space is very simple, it's only have one optima, then we can use gradient method to easily get the global minimum. But if the search space is very, very complex with many with many optimas, and it's hard for us to find a global optimization. So the material problem is actually such kind of a complex problem. So we can utilize the machine learning to solve such kind of a problem. So the machine learning and the statistical inference can make predictions to such a large combination, such large space based on a small amount of existing data. So Y here is the targeted property we care about, and the X here in material science, we call it features or material descriptors. It's like the compositions of the material or the processing condition of the material. And the F is the functional form or the mapping between the X and Y. So we want to utilize the machine learning to give us a accurate F. So if we have the estimation of the property, we can have a quick identification of the material with good property. Or we can make predictions before we do experiment. That will save the cost and the time to make a new material. In the traditional data-driven approach, we need to accumulate a large number of data. And then based on those data, we need to build a machine learning model. Then the model will predict the material properties. Then we can use it to guide our next experiment. So the problem in material science is that we have a very small amount of data available. It's not like the internet problem or the medical problem. We have a large number of labeled observations. But here in experiment, especially in experiment, we only have a very small amount of data. Usually we can have tens or hundreds of labeled data, but the dimension can be very high, can be as large as 20 to 30. So that's the problem in material science. So here, the number of well-labeled samples are very limited. So then based on such a small data, the model is not necessary to be optimal. So usually we have bad machine learning models. So based on such kind of a bad machine learning model, we give the bad predictions. So the guide to the experiment or to the next calculation may not be good. So we do such kind of a iterative loop may not be so efficient. So based on such kind of consideration, we propose such kind of adaptive design loop to accelerate the search for new material with target properties. So we add a panel of adaptive experiment design. So still we start from the database. We form a small amount of data and build the statistical inference or machine learning model. Not just go to the experiment, not directly to experiment. We use an adaptive experimental design panel to help us to design the next experiment, help us to choose the next candidate which have the potential to show good property or have the potential to improve our model. So we choose the candidate and do the experiment or do the calculation, and then feed the data back to the database. So the database have more data, then we retrain the statistical inference and use the adaptive design panel to choose the next candidate again and do the iteration loop again and again to find the new material with targeted property. So the emphasis here is the efficient sampling. So we want the output of the machine learning model is not just the prediction. We want the uncertainties associated with these predictions and utilize both the predictions and the uncertainties. We predict some, we construct some utility functions that help us to search for to recommend us the new material. So here I would like to show a very simple simulated case. So this is not for the experts in machine learning. This is just for students. It's just to show our idea more clearly. So suppose we want to maximize the Y by varying X. We can consider Y is the strength of the material or the ion conductivity of the material, and X is the composition, say like the composition of the aluminum in the titanium. So the question of finding new material is how to find the best X to maximize Y if we only know 3 points. If we know the actual distribution of Y with X, it is quite easy. So we can directly find the X optimized X where the Y is the maximum. But in reality, we don't know the functional form. We don't know the function. So how to find the best X to maximize Y? So we can use the machine learning. So we employ the machine learning. Here we employ the simplest one, the linear model. We can fit a linear model, that's the simplest statistical inference. We usually call it a regressor in our paper or in our work. So based on this regressor, we can predict all the possible X, and the best prediction can be chosen for the next experiment. So the one with red dot is the next point, next experiment we need to do. So after we perform the experiment, which was suggested by the prediction, we found it is actually not good. But good since we have 4 points. So we now use these 4 points to retrain the regressor, and this regressor will suggest a new point for us to do experiment. So we perform the new experiment, but find that the property is not as good as we expect, but good since we have 5 data points. So what we do, we start from data and do the statistical learning, get the regressor, and the regressor suggests us to perform new experiment. And we do this loop again and again to find the best Y or the good Y, good property. Actually, this loop is not very efficient, especially when the data is very small in the beginning. we do the iteration loop again and again. We almost try all the possibilities, and finally we find the best Y, but this is very inefficient, and it's even worse than the random sampling. So similarly, we may use other regressors. For example, we can have more nonlinear one. We can try a polynomial model, but still the loop is not efficient. It takes us too many times to get the best Y. So we can add some physical model or domain knowledge to help us to build a regressor which can have a bad mapping between Y and X, or which can give a bad functional form. So in this case, the number of experiments are greatly reduced. The number of experiments now can be 60. So we tried half of the possibilities. So in this case, it's still not acceptable in material science, especially when we do experiment. We cannot perform so many experiments. It's too time and cost consuming. So here we want to add a experiment design panel. So from data, we build a machine learning model, and then from the machine learning model, we have the predictions. We also have the uncertainties. So we use the experiment design to give the next candidate. Then we do experiment. So again, we use the same linear model, but we use an efficient global optimization algorithm to choose the next experiment. So in this case, we tried only a quarter of all the possibilities. We only use 25 new experiments. We can find the best Y. If we have the polynomial model, we still use the efficient global optimization algorithm to choose the next experiment. We have the 15 new experiment, we can find the best Y. And if we combine them together, we have a better machine learning model, especially from the physical model or domain knowledge. Then we combine the active design, experiment design part. Then we can get the global maximum very fast. As you can see, we can only use 6 new experiments to find the best Y. So in this case, we say that the machine learning tools or informatic tools can accelerate the discovery of a new material in this very simple 1D tool case. And then I would like to show the other two cases, the real cases. We want to employ that kind of iteration loop to design new material. The first case, what I call is selecting the selector. So the problem we want to solve is this. We start from a small amount of data, build the inference model. But then we apply those models to the unexplored all possible candidates, all possible materials. Usually it is very large. So we apply the statistical inference to the unexplored candidates. We have thousands of candidates with predict properties. Then the question is, what we should do next? What candidate should we choose? There are too many candidates, and the inference model we know that is not good. So how to select the candidate for the experiment is what we it's the problem we want to solve. So there are many selecting methods. So we call it selector. So for example, we can randomly select the one and do the experiment. That is try and error. There are some other strategies such as exploration, or the balance off between the exploitation and exploration. So I would like to say something about those different strategies. So the first one is the exploitation. So please see the figure. We have 5 blue dots. Those are our experiment data. If we build a machine learning model based on these 5 blue data, the red one is the machine learning curve. If we suppose that the machine learning is 100% correct, we believe in the machine learning. So the machine learning prediction is the real experiment result. In this case, we choose the best one, the best value suggested by the machine learning. This is one extreme condition. On the other hand, still we start from these 5 blue dots. We build the machine learning model, the red curve, and the gray curves are all other possibilities, are all other possible curves. So if we don't believe in our machine learning model, we think our machine learning model is bad. So we need incorporate more data points to improve the data. So which point should we incorporate? Which point should we end in to improve the machine learning model? It must be the data, the experiment with largest uncertainty. If the machine learning model is not very good there, we give the point there, and this will improve the machine learning model. So this strategy we call exploration. But in reality, we don't know whether our model is good or not, whether it is perfect or whether it is totally bad. So we need some balanced trade-off between the exploitation and exploration. So please find the left-hand figure. So suppose we have 4 new experiments or 4 new samples we need to do experiment to synthesize and to measure. So the y-axis is the property, the property of the material, and the horizontal line, the blue line, is the best so far, is the best performance so far. The height of the bar is the property predicted by the machine learning model. So we think that the prediction may not be accurate. It involves some uncertainties. So the distribution, the Gaussian distribution curve is the uncertainty associated with the prediction. So in this case, we are not believing in the height of the bar, not believing in the predictions. We are not choosing the one with largest uncertainty, but we want to know the possibility if we did the experiment to improve the property. So actually it's the shaded area above the blue line. So if we integrate that area by the property density function, probability density function, so we know the probability if we did, for example, if we did the experiment 3, we know the probability to improve the property, to get a better property than the best so far. So if the probability here is both related with the predicted value and also related with uncertainty. So in this case, we balance trade-off the exploitation and exploration strategy. So based on such kind of strategy, the next experiment not necessarily to be the highest value of the red curve, not necessarily the one with the largest uncertainty. It choose a such a X with some balance trade-off. Okay, then we use a modeled system, barium titanate ferroelectric material, to benchmark our strategy. So the target property we focus on is the electron strain. In this material, if we apply an electric field, we can have the shape change of the material. The material will generate a strain. So we would like the strain to be as larger as possible at a constant electric field so that we can make the device smaller. So the data we have is only 61 with known property. But the search space is very large. We can have different elements to replace the existing element so that we can have, for example, we can have 4 different elements going to different sides of the material. This will allow us to have like about 0.6 million possible material, which we can synthesize in principle. So the problem is how we start from this 61 data to get the better property from those 0.6 million candidates as fast as possible. So this is the feedback loop we use. We start from database, the panel 1, and we build the inference model, the panel 2, and we apply the inference model to all the possible compounds. Then we have the predictions and the uncertainties. So we use four different strategies or algorithms to choose the next experiment. Each strategy will choose one particular material, and then we really made the material and synthesize the material and do the measurement, and then feed the data back to the original data set and do this loop again and again. Our goal here is to find a good material, and the second goal is to compare which selector, which algorithm is the best one to recommend the next experiment. So here we build the very traditional, very simple machine learning models such as the linear model, polynomial model, as a support vector machine. And then we choose the one with best performance in the training data and also in terms of the CV error. And then this is our iteration results. This is, please find the left-hand panel, the left-hand figure. So the x-axis is the iterations, and the y-axis is the measured string. So for iteration 0, that's all our training data. And the horizontal line is the best one in our training set. And then we do the first iteration. We employed 4 different algorithms to suggest the next candidate. And we find that the trade-off between the exploration and exploitation suggests the best material. And we really did the experiment and find it is the largest. And then we've put these 4 data back to the original data set and retrain the model and use these 4 different algorithms to suggest the experiment again. And we find that the trade-off, the red one, still the best one. And we do the loop again and again. We find that the trade-off algorithm always suggests the best performer. So in this case, we only have 3 new experiments. We can improve the property by 50%. The blue curve is the best so far in the training data, and the red curve is what we obtained. And you will see the gray one behind the blue curve. That is the best one reported in this group of materials. So we say that using the machine learning together with experiment design algorithms will largely accelerate the discovery process. And then we use some DFT and phase field simulations to explain why the property is large in this particular material. And then we show another case study, and we show this in a chip memory alloy. This is very similar material, but it converts the thermal energy into mechanical energy. And the mechanism of the functional properties in this such kind of alloys is the Martensitic transformation. So the transformation is actually the very first order transition. This large thermal hysteresis between heating and cooling will cause very bad fatigue properties. So what we want is a smaller hysteresis. So our design target is to search for smaller thermal hysteresis in these kind of materials. The tuning knob here is still the chemical compositions. We can use different elements to replace the existing one. And in this case, we may have like 0.8 million possibilities, but we only know 22. So we build the statistical inference based on these 22 data point, and then use adaptive design to suggest next candidates and do the iterations. So because there are so many machine learning models and so many selectors, so we want to utilize our training data using the resampling method to find the best combinations of the regressor and the selectors for our particular problem. So in this case, we find the spot vector machine, the SVR, together with the efficient global optimization can give the best results, can give us the smallest number of a new experiment to find the best material. So this is our iteration results. In this case, we are finding the lowest value. So the property here is the low, the better. Again, we utilize like 6 new iterations. We find the very good new material. This material, at least at that time, is the best in the world. So, and the functional fatigue problem property is also improved. For example, please see the D1, the figure D1. The traditional material can have 25 Kelvin shift of the temperature, but in our case, we only have 0.01. It's a very negligible shift of the transformation temperature. So here is a summary of our work. We would like to say that the use uncertainties in the measurements, also in the predictions, can help us to accelerate the discovery of new materials. And our focus here is to iteratively refine the predictions to minimize the new experiments or calculations when we do the experiment. Okay, that's all. Thank you. Thank you very much.
Okay, thank you, Dustin, for this wonderful talk.
Thank you.
Do we have questions? Yeah, this is actually, I think this is a very general issue for applying machine learning to science research, because in the industry, many problems we have lot of data, right? But in many scientific problem, actually, not only for material research, like in quantum, all kinds of quantum physics, which I'm familiar with, maybe also in other fields, we don't have lots of data to deal with, at least not as large as in some industry applications.
Right.
But maybe in some other fields they can, like in astrophysics, they do have lots of data, but not for all scientific applications, right? So yes. I think that's a general problem when we try to combine the machine learning with scientific discovery. We always face the problem that in many situations we don't have lots of data. I think that's a general issue. Yeah, probably was efforts for people from different fields to think about that, right?
Yeah. Right. Yes.
So I have a question, if I may. So have you thought about augmenting the experimental data with calculated data?
Oh, all my data is from experiment. So because I'm an experimentalist, so all these data are from my lab. So we did all the experiment by ourselves.
Right, understood. But could you not augment your data with theoretical data?
Well, it's hard, you know. There's some deviation from the theoretical one and the experimental one. But yes, that's a very good suggestion.
I see.
You know, its calculations have more data, but it may not so accurate, but it can give some tendency, so we can bind them together, right? Yes.
Right. And may I ask a second question? How do you represent in your machine learning model the different materials? I mean, what is your descriptor?
Oh, okay. So here we use some, like, we use the traditional one, some properties of the element, like the radius of the element, or the electronegativity or valence electron numbers, all those descriptors to represent the particular material. And we do the mole fraction for different compositions.
Thank you.
Yes, actually, for the first question, I have one thing to add. Actually, Yi Zhuang and I, we just had a paper early this year. This is the idea of using theoretical simulated data to train neural network and then apply to. Actually, in our case, we apply to some experimental this STM imaging to find out some physics from the experimental data.
Yes.
So basically, the idea is we train the neural network with some simulated data, but then after training, we try to apply the neural network to recognize some patterns or features in the experimental data obtained by this STM experiments. But there we also realize the problem we just mentioned, that indeed there are difference between simulated data and the real experimental data. In particular, there are some detailed structures which cannot be captured by the calculation, because the calculation can always just capture most the universal part, and there are always some details that cannot be captured by the simulated data. And therefore, if we train the neural network with this simulated data, at some point the neural network will get confused when because the difference between.
We also tried this. We use the microstructure generated from the micron magnet simulation, and train the neural network to recognize the skymings. So, and we apply them to the STM image, and we find some good results. And later I can share the paper to you and ask for some suggestions.
But in the paper we wrote with Yi Zhuang, we also invent a method to deal to deal with this difference between simulated data and experimental data.
I will try to find out.
We try to there's some trick we try to play with to solve this problem.
Yeah, this is a very interesting problem.
Yeah, and that's actually related to the top thing we discussed when we don't have on the situation we don't have lots of data, whether we can use simulated data, right? But there are also problems about this approach.
Yeah.
Okay, maybe the time to move on to the last talk. I think unfortunately Professor Ge Wang cannot give the talk today here, and his talk is on record, right? So I think
we have a video to launch from his presentation, so I will just do that.
So please launch the video. Thank you.
I think while I'm pulling up the video, there was one more question that is in the chat function that you can see there.
I don't see the question in the chat. So I don't see anything in the chat.
No.
It came in from Yu Zhang himself, actually. It says, how do you estimate the uncertainty of the prediction?
Okay.
Chat. Oh, chat. Yes.
Okay. So in our case, the question is for me, right?
Yeah, question
Yes,
from
it is.
Yi
Yeah.
Zhuang to Zheng. Yes. How to estimate the uncertainty of predictions?
In our case, we use the resampling method. We do the bootstrap to get the bootstrapped data set to train like 1,000 different learners to get the estimation of the uncertainty. But actually, we can use the Bayesian
Muted
model to directly get the uncertainty.
He's giving us a thumbs up. I think that answered it.
Okay.
Okay. All right. We'll move on to the video now then from the presentation from Professor Wang.
Good morning. So I will make a presentation on MLST for medical physics. So MLST stands for the title of our new journal, Machine Learning Science and Technology. We try to promote this journal, and my talk will focus on medical physics. So I will talk about 4 points. Start also with MLST and for the 4 points. So first, the medical physics, and the medical physics is a very important area, and my career is in this field. And the AAPM means American Association Physicists in Medicine, and we saw the rapid growth of the field, and right now the membership is about 10,000. I have been a member for many years.
Working now?
Earlier my career, I got a travel award. I gave lectures in Europe, and this is a part of my finest memory. And I know a little bit about the field, and we have a flagship journal, Medical Physics. The readership pretty much 3 categories: engineers, biologists, and other scientists. We have a medical physicist, either in imaging or therapy area. And also we have a lot of medical doctors, physicians. So this is a very good journal, and we basically focus on intersection between medical physicists and the engineers and the scientists. Also, we have another journal called Journal of Applied Clinical Medical Physics. So that is more clinically orientated. So we focus on this part. So physicians will contribute papers, or we wrote papers directly related to clinical practice. So both journals are very popular, and the journals have an international scope. So majority articles from American, and the mainland of China contribute a lot. So say medical physics authorship, and the Chinese scholars, and the second to that in United States. And for the applied medical physics journal, again, the mainland of China has a huge contribution,
Yeah,
only
we
second
lost
to
Jessica.
Japan. Both
Is
journals
she
well known,
playing?
so very decent, decent quality. So here you see some statistics. On average, each article, let me just magnify a little bit. So each article and will get yearly average number of citations about 4 or 5, something like that. The clinical journal, clinical counterpart, number of citations a little bit lower, but still very good. And our sister journal, I mean medical physics, is a United States based. A sister journal called, let me just magnify, called Physics in Medicine and Biology, known as PMB, also a very good journal. So they are very much comparable, as you see the biometric measurements here. So this is an overall field, well established, and we have very good readership, well-defined research directions, and a very clear clinical utility. So this is something very general about medical physics. Second part, we talk about learning revolution, related to AI, machine learning, particularly deep learning. So we know and we have experienced great development in information technology. And earlier than that, we have so-called industrial revolution, and engine and those things. So we have been able to extend our physical capabilities and our sensory organs, and with telescope, microscope, engine, and we can walk much faster by train or take an airplane. And the new revolution, also called IT technology, but not information technology, not industrial technology, rather intelligence technology. So we use machine learning algorithm, particularly deep learning. Very much we can mimic human reasoning process and data extraction capability. And the deep learning has been very hard for past several years due to high performance computing power and the availability of big data and smart algorithms. So we can use deep learning for medical imaging as well. So we did some literature search and see just use key phrase deep learning medical imaging, and with web of knowledge search, we see a rapid growth in terms of number of papers. So you see from several years ago, and we start getting good results. So number of groups rapidly increased. So this is very encouraging. In 2016, I wrote a perspective article on deep imaging. So we talk about a big picture and our field development. So traditionally, we do data analysis, image analysis using classical algorithm, and we reconstruct the image using either analytic or filtered back projection algorithm. We can also use statistical algorithm. And now with deep neural network, we could imagine that we do image reconstruction from data to image domain, so along this green arrow. And also we can use neural network to perform image segmentation and image classification. And we can just integrate two processes together. And from X-ray raw data, we can directly extract diagnostic features. In long run, we could use images to guide surgery, robotic surgery. So this is a great future of precision imaging or medicine. And we edited the first IEEE special issue on deep tomographic reconstruction. And recently we wrote a review article to synthesize medical imaging and radiotherapy with deep learning. And we think some picture like this, imaging is not just studied alone. And in the context of radiation therapy, we get a lot of information and clinical data, reader report. We can use natural language processing technique to extract semantic graphs. So all these things linking together, and the whole medical treatment process and can be integrated in the AI framework. So these deep learning, machine learning opportunities are so huge. Many groups become interested, and the journal is created to take the opportunity. So we try to invite medical physics papers that use machine learning technology. So let me just show you some selected projects we are doing using machine learning for either therapy, radiation therapy, dosimetry, or medical imaging. So just to give you some general idea. And we tried to use deep learning, particularly denoising convolutional neural network, to accelerate Monte Carlo simulation. Then we can perform individualized patient dose estimation from X-ray CT scan. So this work was done by Professor George Xu's group in collaboration with my group and others. And also we are in collaboration with General Electric and Harvard Medical School Radiation Oncology Department, try to use deep learning algorithms to remove CT metal artifacts so that we can have a quantitative estimation of attenuation background, which is needed by proton therapy. So we can estimate attenuation background so that we can deliver therapeutic radiation dose to tumors. So this is a therapeutic application. Another interesting application is how to remove image noise from low dose CT scan. So CT data contain Poisson noise, and lower dose is stronger noise. So with deep neural network like this, and we can perform a low dose scan and obtain very noisy image, go through neural network, and we remove noise, pretty much keep subtle structures in good comparison to high quality full dose CT scan. And we are collaborating with colleagues and also industrial developers. And GE Healthcare developed the low dose CT denoiser and received FDA approval. So we are working with GE Healthcare and the Global Research Center very closely. And last year we wrote an article published in Nature Machine Intelligence, and the work is deep learning based image denoising. But what we do is a little bit different from other neural network. You do direct mapping. So what we did, and we designed modularized adaptive processing unit. So we do denoising step by step. Then we ask radiologists to select optimal steps. So we get the best diagnostic performance. So this adaptive processing network was compared with commercial CT reconstruction algorithms that use iterative reconstruction algorithms. So we performed a double-blind study and we show systematically that deep learning algorithm can consistently outperform or just deliver a similar performance like traditional iterative reconstruction algorithm. So this is a very interesting finding that shows deep learning has a potential to take over traditional iterative reconstruction algorithm for low-dose CT application. And recently, we got a paper published in Nature, which is an open data science oriented journal under Cell Prize. And in this article, we performed virtual monochromatic CT imaging. So traditionally, you use zero energy CT scan, and you could use two X-ray tubes emitting different X-ray spectra. And instead of using two X-ray tubes, and this technology could convert CT data from single X-ray spectrum and to monochromatic, virtual monochromatic CT images. So in simple way, it says, and we could use deep learning and produce the same or equivalent amount of information zero energy CT scanner could deliver, but we only use a relatively cheaper single source, single spectral X-ray data set. And the X-ray imaging is very important, and other imaging modalities also complementary and critically needed for clinical imaging, like MRI, like ultrasound, nuclear imaging, so on. Another project we are very interested is to build a hybrid CT scanner which could perform CT and MRI scans together simultaneously. So this is just a system design. And the cheaper version would look like something extended C-arm. Traditional C-arm machine can only perform X-ray cone beam scans. But with extended design, we can imagine we can perform both CT scan and MRI scan. So we got double helical data stream, deliver CT and MRI information simultaneously. So this will be something important for like stroke imaging or just the battlefield imaging in collaboration with UT Southwestern. And we are working on MRI guided radiotherapy. So we use a small interior MRI system to get a tumor image while we plan radiation treatment schemes. So a lot of opportunities along this line. And we believe medical physics is such a broad field. In addition to a limited number of projects we performed, there are huge opportunities. The journal would welcome your submissions, your inquiries, or collaborations. The last point and is really kind of a conclusion. We believe together each achieves more. The put together called a team, and with the strong momentum of deep learning, and we see next several years will be great for machine learning based research, particularly in medical physics domain. And using the software called Google Trends, you could just see trending things. And I put deep learning into the software, then I see the popularity, the frequency of the words. So the deep learning has been around for a while, then all of a sudden getting rapid growth and stabilize. That means the field remains very hot like this. And at this point, the field taking off is around 2016, that is when I wrote the perspective article on deep imaging. So we see the field grow very fast. So in this context, so our journal, MLST, Machine Learning Science and Technology, covers both scientific applications and also conceptual advances. So a lot of things and you do or we do could submit to this high quality, rapid open access journal. So let me just say a little bit about the editorship. I'm very interested in scientific publication, and I'm currently involved in this IOP journal, MLST. Also, I'm on editorial board for IEEE Access Journal, IEEE Access with impact factor, I think little over 4. A new journal I mentioned and under sale price called Patents. This is science dedicated to science of data. I'm on advisory board. So I enjoy doing open access, machine learning, editing, reviewing those things. So welcome your inquiry and collaboration. You can just search my name, and I work with Rensselaer Polytechnic Institute, and my university is private, relatively small, but we are the very first technological university in English-speaking countries. So we have a very long history, and we focus on biomedical imaging research as related to medical physics. So this is just my intention, open to collaboration, and hope you will submit your good papers to this IOP journal and as related to medical physics. This IEEE access is just too wide, not dedicated to medical physics. And I have a strong feeling medical physics work will be best suited for machine learning science and technology, and a lot of physicists, different areas, all covered by this journal. And this open access journal by IEEE got a decent impact factor. But as I just mentioned, the journal covers all the branches. And machine learning is very hard. And the IOP journal dedicated to machine learning. So I have a feeling the impact factor of this machine learning science and technology journal will be a little higher than that of IEEE access. So just share with you my opinion on this new journal. So hope you like it. Okay, this last slide and another related thing. I also work with IOP Institute of Physics Publishing. So work with IOP on a book series. Under the theme AI in Biomedical Sciences. So if you click this website, not see very clearly, but see this is a website, okay? You can see information about another IOP book series. The theme is next generation computing, and we do on a complementary topic, AI in biomedical sciences. This is a big field. We expect a good number of books will be published along this direction, either authored, co-authored, or edited. We welcome. If you are interested, feel free to send me email. We can discuss a specific topic. So you can write dedicated or edit dedicated books for this book series. Anyway, so this is my brief presentation. You search my name, you can find my email address. And the first slide, you see the URL, my lab, and my imaging center. Thank you so much for your time. Okay.
Okay. Okay. We actually have one more question for Dezhen. Is Dezhen here?
Yes, I'm here. Yeah.
Yes. It's a question for you actually. It's about a question about whether we can represent the material in a 2D array such that we can do convolutional neural network. That's a question from Koshel. Do you have anything to say about that?
Okay. So for one particular material, we can have like different descriptors, different features. I think it's possible to have the 2D array. For material different compositions, we can have like if we have 2 elements varying, then we can have 2D matrix for that material, that kind of material. If we have more elements, then we can have higher arrays to represent. I think it's possible. It's just my opinion.
Yeah, I think. All right. Okay. Yeah, I think there are many different kinds of machine learning algorithms, and also there are all kinds of scientific problems. So we need to actually do a match, right? So this really need maybe a new generation of students who can have knowledge on both sides. On one hand, they have a very good understanding of the scientific problems, and on the other hand, also know a lot of different kinds of machine learning, recent advances in machine learning algorithms, and they can put a best match between algorithms and the scientific problems. I think that's the best way to move the field forward. So is there any other questions from the panelists or anything people want to say?
Maybe let me double down on this. I fully agree. I think these talks have really wonderfully shown the potential of these statistical learning methods, and I also fully agree that it's a dual thing, right? To me it reminds me a little bit of learning how to program, which also now is pervasive in all the different sciences, right? And it's just an enabling tool, which is state of the art, and so to have programming skills is something anybody should have on top of gaining the specific expertise of one scientific field or the other. So I think that machine learning expertise should be developed in the same sense. So you start out from a certain field, and then you use machine learning. Just like 30 years ago, people would start using programming in their fields.
Yeah. Yeah. So I think the one key message is that this new journal, Machine Learning and Science and Technology, is a good platform, right, to help in this process to bridge the computer science development of machine learning and the scientific discovery. So yeah, and really it's a dual process, right? We can use the scientific ideas to motivate the development of machine learning, and we can also use machine learning to help scientific discoveries. So yeah, I think that's a benefit of both. And if you have good papers on this, dual process, you can consider to submit to this journal. Yes, we have. So, is there any other question or comment from publisher or from other people? If not, maybe
there's another question that's come in onto the question panel.
Oh yeah, another question coming on. Okay. How about what PET image? What I don't know what the question means. How about the what?
So how about the DI in PET imaging or DL in PET imaging? Maybe that's one for Professor Wang, perhaps.
I don't know who should answer this question.
I think that might be one for Professor Wang, so we can get that answered afterwards and send that through.
Yeah. Okay. Maybe if not, I think we should thank all the speakers in the afternoon. Is that time to say goodbye and to conclude this wonderful event?
Thank you all. It was wonderful.
Thank you very much.
Bye-bye.
Yeah, thank you very much, everyone. We will be posting the recording afterwards if anyone wants to kind of rewatch it, and a survey will be launching as well now as everyone kind of leaves the webinar. So please do feel free to fill that out. And yeah, thank you for everyone for our chair today and for the panelists. Much appreciated. It was a really great event. So thank you very much for taking part.
Okay, good. Bye-bye.
Bye-bye.